Hello, RubyConf. My name's Tom. I'm a senior staff engineer at Shopify, and I'm here to talk to you about programming with something. Almost exactly 10 years ago, right at the end of October 2011, I gave a talk called Programming with Nothing at the RubyMana conference in London. Now, the details of that talk aren't important. You can watch it if you're interested in understanding it, but I'll very briefly summarize its conclusion so that I can build on it today. In that talk, I showed that we can still write useful programs in Ruby if we only allow ourselves to create procs and call procs. And that's because, it turns out, we can use procs to encode any data structure and then also use procs to implement operations on those encoded data structures. For example, here's one way to encode a number as a proc that you call once with a function p, then again with an argument x, and it calls p on x a fixed number of times. So the encoding of the number 3 calls p 3 times. If you're not familiar with the pointy arrow and square brackets syntax, it's just a more compact way of writing lambda and call, and I'm using it here to keep the code short and tidy. Not surprisingly, this encoding lets us represent numbers that are as large as we like 5 or 15 or 100. These encodings are legitimate because there's a way to convert them back into Ruby numbers whenever we like. If we take the Ruby proc that adds 1 to its argument and call it on the Ruby 0 object 3 times, we get the Ruby 3 object. And the same thing works for 100. If we call it 0 times, then we just get the original Ruby 0 object back. The encodings of numbers are not only legitimate, they're also usable for computation because we can implement operations like increment, decrement, add, and subtract in the same way. These are a little complex, so I won't go into the details, but what's important is that they work. I can add an encoded 5 and 3 together to get an encoded 8, and then check its Ruby value to prove the computation happened correctly. Similarly, I can raise an encoded 2 to the power of an encoded 8, and when I decode it, I get the Ruby number 256 as expected. We can encode more complex data structures like pairs and lists, including operations like checking for the empty list or fetching the first list item or the rest of the items, and more complex operations like generating an encoded list of all encoded numbers within a certain range of values, or mapping an arbitrary function over an encoded list. And that gives us everything we need to entirely implement FizzBuzz with all its data and operations encoded as procs. And at the end of the Programming with Nothing talk, I show that we can inline expand all these constants which represent other procs to get a complete FizzBuzz implementation, which is syntactically just procs. Now, I can show that works by pasting it into a terminal and using some helper methods to decode it into a Ruby array of Ruby strings. There you go. It slows down a bit towards the end as the numbers get larger, but it takes about 18 seconds to print them all. So it's 10 years later, and I'd like to pull on this thread a little more. That talk showed that an extremely minimal subset of Ruby is still a fully capable programming language, so we're getting essentially all the computational power of Ruby while only relying on a tiny fraction of its features. In this talk, I'd like us to better understand that fraction by actually implementing it ourselves from scratch. And that means asking 3 questions. Firstly, could we represent these encoded values ourselves? Instead of using procs with their built-in behavior to represent numbers and lists and stuff, could we design and implement our own objects to do it? Secondly, if we have our own objects for encoding values, can we explicitly evaluate them and recreate the computational behavior that we get for free with procs? And finally, if we do manage to recreate that behavior and perform computations with our objects, can we decode the results back into useful information afterwards? If we could do all 3 of these things, we'd no longer be relying on Ruby's built-in implementation of procs to bring our encodings to life. We'd have constructed our own implementation that we can understand and control, and I think that would be pretty cool. So let's start with that first question. Could we represent these encoded values ourselves? Can we roll our sleeves up and construct our own honest, hard-working, artisanal data structure to represent encoded values, instead of lounging around expecting Ruby to be cool with us taking as many procs as we like and using them to represent whatever we want to? Well, Yeah, I think we probably can because, well, let's think about some arbitrary Ruby value encoded as procs. This was our encoding of the number 3. Now, appropriately enough, there are really only 3 kinds of syntax appearing here. Firstly, there are some variables. There are 4 of them here, 1, 2, 3 named p, and 1 named x. Secondly, there are 3 calls, this one, and this one. And finally, there are 2 proc definitions, each with a parameter name and a body. There's this outer one with the parameter name p, whose body is another proc definition, and this inner one with the parameter name x, whose body is those 3 nested calls. Notice that the parameter name isn't a variable, even though syntactically it looks like a variable because it's just a bare name. It's a special bit of syntax for proc definitions to specify the name of the proc's parameter, just like how a method parameter isn't a variable itself, but creates a local variable of the same name inside the method. Variables inside the proc body here can use the parameter's name to retrieve the value of that proc's argument when it gets called. So the variable named x in the body is referring to the parameter named x of the inner proc, and all these variables named p are referring to the parameter named p of the outer proc. And names are how connections get kind of wired up inside the structure of an expression, and it's the flexibility of this wiring up of connections that really gives procs enough computational power to do all the stuff from the previous talk. So the simplicity of this setup is good news, because if we want to represent an expression like this, we only need to worry about representing variables, calls, and definitions, because those are the only 3 structural features that you see in any of these encoded values, even a really big one, like FizzBuzz. So you can think of this as a huge wiring diagram that connects parameters to variables in an intricate and very specific way to achieve its computational behavior. We can make our own representation out of structs. We need classes for variables, calls, and definitions, each with the relevant members. A variable just has a name, a call has a receiver and an argument, the receiver is the thing being called and the argument is the value being passed to it, and a proc definition has a parameter name and a body. To make these structs easier to work with, we can implement the inspect method on each class, so their instances get formatted nicely when we look at them in IRB. Now we can make a new variable whose name is x, or a new call whose receiver and argument are that variable x, or a new definition whose body is that call. And they look superficially just like the real thing, because those inspect methods format them to look like Ruby source code, but they're not real variables or procs, they're structures made out of objects whose behavior we control. As another example, we can make a big inline structure like this to represent the encoding of the number 3. Now, if we look at the shape of this 3 object, it's really a tree structure. There's a top-level definition, and within that we have a parameter name and another definition, and then within that we have another parameter name and a call, then inside that there are some nested calls and variables. We usually call this kind of structure an abstract syntax tree, so this is the abstract syntax tree of the proc encoding of the number 3. Okay. Representing these encoded values as trees is not difficult, but if we already have one of these encoded values as a Ruby proc object in memory, like the number 3 or FizzBuzz or whatever, how can we convert it into our abstract syntax tree representation? Now, I can think of a couple of hacky ways of doing this. One way is to ask MRI for the yarv bytecode instructions, which we could presumably walk over and figure out the structure of the proc somehow. Or we could use the disassemble method to generate the human readable version and process that somehow. Or if the proc got loaded from a file, we could use source location to find out which line in which file, and then read it in as a string, and then use Ripper from the standard library to parse that string into a structure that we can examine. But I don't think either of these options is very good. The first one only works on MRI because yarv is MRI specific. The second one only works if we have the source code of our proc available as a file, which in general we might not if it's been constructed at runtime. So I'm going to suggest a third option, which is to use the behavior of a proc to reveal its inner structure. And that means we're only relying on the functionality of the proc itself and not making any assumptions about where the proc came from or the availability of implementation-specific Ruby internals. If we take a proc like 3, we can already ask Ruby about its parameters. This is telling us that it's got one required parameter whose name is p. So it's easy to pull out that parameter name, which is half of what we want to know about the proc, but how do we get its body? Well, let's think about the easier case of a proc called identity, which just returns its argument. All we know from the outside is that its parameter is called x. We can't retrieve its body directly, but we do know that when we call it, whatever argument we pass in is going to replace all of the occurrences of x in its body. So if we make a variable called x that we want to represent the occurrences of the parameter, and remember that here we're looking at an instance of the variable class we defined, we can call the proc with that variable and get back its body, which is just our variable object x again. So we've learned that the proc's parameter is called x and its body is the variable x, which is correct. Here's another example, a proc called omega, which calls its argument with itself. We can do the same trick and make a variable with the same name as its parameter, but when we try to call that proc with that variable, we get an exception because the body is calling the square brackets method on the variable we passed in. But because the variable is a struct, that means we're getting the struct square brackets method, which fetches the value of the member at a particular numeric index. But we can take advantage of this by redefining the square brackets method on the variable class so that instead of calling anything, it just builds a new call object, which remembers the variable itself and the argument that was passed in. So now, if we call the proc again, we get back a representation of its body. Nice. Finally, let's try with the proc encoding of 3. We can make a variable p and call the proc with the variable as its argument, and we get another proc back because that's what the body of 3 is. Fair enough. We can just do the same thing again, make another variable from its parameter, called x this time, and call the inner proc with that variable, and we get back the body of the inner proc. Great. That gives us all the information we need to completely reconstruct the original Ruby proc with our own representation. So we just have to wrap that technique up into a method. Don't worry about trying to read any of the code I'm showing here. It's all on GitHub if you're interested, so it's safe to just let it wash over you right now. But the overall idea is that we can write a fromProc method which converts a proc into an expression. We do this trick of making a new variable object with the same name as the proc's parameter and calling the proc with it as an argument, so that all the occurrences of the proc's parameter inside its body become that variable object. Then we recursively convert the result, just in case the body of the proc is another proc, and finally we build a new definition object and return it. And as we just saw, to make this work properly, we need to replace the square brackets method on the variable call and proc classes to convert the receiver and argument from procs using the method we just defined, and then wrap up the resulting expressions in a new call object. I've picked those 3 classes because they're the 3 kinds of thing that can appear as the receiver of the square brackets method inside a proc that we're converting. So if we evaluate any proc body which contains a call, it'll use this replacement method which builds an instance of our call class instead of actually calling anything. And just bear in mind that in production code, we'd need to remove these monkey patches afterwards, or else they'll probably wreak havoc with other bits of code that expect the original methods to be there. Now we can convert the proc encoding of 3 to our own representation. You can see that that's an instance of our definition class. And likewise for the proc encoding of fizzbuzz, there's our converted version, and that's a definition object too. All right, so now we have our own representation of these proc encodings. Can we do the work of evaluating them ourselves so that we're not relying on the behavior of Ruby procs to compute 2 plus 3 or fizzbuzz or whatever? That would mean implementing some method called evaluate that can take an abstract syntax tree called expression and, evaluate it somehow. But it's not very obvious what that means. A variable will refer to the parameter of some proc that it's inside, so maybe we can get an argument that way, and a call will have a receiver, an argument that need to be evaluated somehow, and then we do something with them, I don't know what. And for a definition, we need to evaluate its body at some point, but not right away, only when it appears as part of a call somewhere else. This all seems a bit complicated, and I'm afraid that I'm not clever enough to work it out myself. But fortunately, a mathematician called Alonzo Church wrote a paper in 1935 that explains how to do it. And this paper was Church's approach to the same decision problem that Alan Turing tackled by inventing Turing machines in a paper he published the following year. It's got tons of good stuff in it, even though it's over 85 years old. For example, there are some cool ideas about how to represent numbers as expressions that look like procs, which is ultimately the source of my entire previous talk. So thanks, Alonso, appreciate it. But there's also this bit about operations we can perform on these expressions. Operation number 2 here is called reduction. And in our Rubyist understanding, it's talking about what to do when you call a proc with an argument. This notation here says that the way to evaluate that call is to replace all occurrences of the variable named x in the expression m with the expression n. X is the name of the proc's parameter, m is the body of the proc we're calling, and n is the argument we're calling it with. So according to Church, replacing occurrences of variables inside proc bodies is pretty much all we need to implement. Let's briefly look at this reduction idea in the world of normal Ruby procs to see why it's relevant. Say we have this proc p, which takes a greeting and a name, and returns this interpolated string. If I call it with the string hello, then we just get another proc back, but conceptually what's happened here is that the string hello has replaced the variable greeting in the body of p. So you can think of this result as being the body of p with one of its variables filled in with a value. And then if we supply a second argument, the string rubyconf, we get back that inner string with both variables replaced with the two strings we passed in as arguments. In his 1935 paper, Church is saying that when we have a bunch of proc definitions and calls all stacked up together to make a big expression, if we perform this reduction operation repeatedly, we're getting closer to turning that expression into a fully evaluated result. And I'm going to quickly show you how we implement this operation on our abstract syntax tree representation. First, we need this helper method called replace, which takes the name of the variable to replace and an expression to replace it with, and some original expression that we're performing that replacement on. It recursively walks down the abstract syntax tree of that expression, and when it finds a variable whose name matches the one we're looking for, by using the pinned name syntax in the first pattern there, which will only match if the variable's name is equal to the name we're replacing, it'll return the replacement expression instead of the original variable. One interesting case is when it finds a definition whose parameter name clashes with the name we're replacing. At that point, it just stops searching and returns the original definition, because any variables with that name inside the definition's body must be references to its parameter, so we shouldn't mess with them. As a footnote, please be aware that we would need a more complex implementation if the replacement might contain variables whose names don't refer to any parameter, which is why that Church paper says we can only do this replacement provided that the bound variables are distinct. But we don't have that problem in any of the expressions we're evaluating, so in this specific situation we can get away with something simpler. Here's the replace method in action. If we make three variables called a, b, and c, and make an expression that calls a with b and c as arguments, we can use the replace operation to replace b with some other expression, like the identity proc we saw earlier. Or we could replace a or replace c instead to get different expressions where the variable a or c has been replaced. Once we have this replace operation, we can use it to reduce an expression by finding opportunities inside that expression to pull out the body of a definition and replace its variables with something else. First, we need another helper to decide whether an expression is a value, something that's a successful result of evaluation. We're getting procs to encode values here, so only proc definitions get to be a value. Calls and variables aren't values. And then we can finally implement that Alonso Church reduction operation on expressions. Now, because Ruby uses a left-to-right call-by-value evaluation strategy, we have to do a bit of work to find the next part of the expression to reduce in the same order that Ruby would, so that we're correctly reproducing its behavior. In the general case, we reduce the left-hand side of the call, which is the receiver. If the receiver is already a fully reduced value, then we reduce the right-hand side of the call instead, which is the argument. And then only in the special case when the receiver is definitely a definition and the argument is a value, do we replace the parameter with the argument inside the receiver's body, which is what Church said we should do. To actually evaluate an expression, we just repeatedly reduce it. If I make expressions for add 1 and 2, and then make an expression which calls add with 1 and 2 as arguments, I can keep reducing it over and over. If none of the patterns inside the reduce method match, there's no more reducing we can do, so evaluation is done. You can see here that we ended up with a definition at the top level, but Church only told us how to reduce calls by doing some variable replacement on the body of the receiver, so it makes sense that we have to stop here. And that's easy to wrap up as an evaluate method. We just keep calling the reduce method until none of the patterns inside it match. And that lets us evaluate the whole thing in a single step. So, great. We've successfully represented and evaluated these values. So the third problem is how we decode the final results of evaluation to make sense of them. I don't know if you noticed, but when we added 1 and 2 just now, we got a result that doesn't look the same as the encoded 3 we saw earlier. And that's kind of a problem because these encoded values are only useful if we can decode them back into their Ruby counterparts. But if this abstract syntax tree doesn't match our idea of what 3 looks like, how are we meant to identify it as the number 3? To make this work, we need to introduce the idea of a constant, which is a sort of atomic value that we can pass around even though it doesn't have any behavior. So our abstract syntax trees will contain constants as well as variables, calls, and definitions. Constants have names just like variables do, but unlike variables, they don't mean anything. They just sit there being whatever constant they are. For constants to be useful, we need to add support for evaluating them. First, we need to extend the value predicate to treat constants as values, as well as any calls where a constant is the receiver. Because constants don't have any behavior, we want them to just sit there and be inert if anything tries to call them with an argument. But now, if we take the result of adding 1 and 2 and call it with 2 constants, I'm calling them increment and 0, but the names can be anything, then when we evaluate that, we get this result. You can see that evaluation treats constants as inert values and leaves them alone, which allows them to pile up in a structure that we can then recognize. In this case, we can see that when 3 is called with arguments, it calls the first argument on the second argument 3 times. And that result is easy to recognize as the number 3, even though the original expression wasn't. Here's how we implement that conversion. First, we build and evaluate an expression which calls the encoded number with 2 constants that we can recognize later, and then we iterate over the structure of the result to count how many times we see the first constant. And if we call that conversion method on an encoded number, we get the correct Ruby integer back, even though the structure of the encoded number might be more complicated than its simplest possible representation. Okay, we've asked, could we represent, evaluate, and decode these proc encoded values ourselves instead of relying on Ruby's proc implementation to do the work for us? And thankfully, the answer to all of these is yes. That's a cool result, and I want to believe it retroactively justifies the pain of programming with nothing in the first place by limiting ourselves to writing programs in such a restricted subset of Ruby. We've created the opportunity to fully understand and implement that subset ourselves from scratch. To me, it feels empowering to have that level of insight into and control over the actual machinery that's doing the computation, not just the programs we run on top of it. Here's a quick demo of converting the FizzBuzz proc into an abstract syntax tree and then interpreting that as an array of strings, which uses our evaluate method to convert the expression. As you can see, it works fine, although unfortunately it's a bit slow. It takes almost 2 hours to finish printing all the numbers up to 100, which isn't super practical. So it's natural to ask, could we make this faster? Our approach takes 2 hours to execute FizzBuzz versus about 18 seconds for the native Ruby procs. It's cool that we can do evaluation entirely on our own, but it would be nice if we could speed it up a bit. Again, fortunately, in 1964, a computer scientist called Peter Landin wrote a paper called The Mechanical Evaluation of Expressions, which solved this problem. This paper gives the specification of what we would now call an abstract machine for evaluating expressions, where the state of the machine is these 4 data structures called stack, environment, control, and dump, which is why it's now known as the SECD machine. The most important part here is the control, which is a list of commands waiting to be executed, whereas the stack is a list of intermediate evaluation results. Each step of the machine updates parts of its state according to mainly the control, which says what to do next. It was an incredibly influential contribution to show a toy machine that can evaluate expressions efficiently like this. I don't have time to show you all the details, but here's the bird's eye view of how it works. What makes our implementation slow is all the reducing. We're constantly rewriting the expression to replace variables with other larger expressions, and eventually the expressions get huge and it takes ages to do anything to them. Landin's idea was instead to have the machine maintain something called an environment that remembers the names and values of all the variables currently in scope. And then we don't need to do any rewriting. We leave the expressions alone, but just keep adding more names and values to the environment as we need to. So if we want to evaluate a proc definition being called with an argument, we just pull out the body of that definition and make a new environment that remembers that the parameter x should always have the value of whatever the argument was. And then we just evaluate the body of the definition in that environment. So we haven't had to rewrite anything, we've just remembered the value of parameter x. So if we ever evaluate an occurrence of the variable x inside the body, we can retrieve its value from the environment. To make this environment idea work, the machine has to be careful about evaluating definitions because the variable bindings in the current environment will probably be needed to evaluate the body of the definition later if it gets called. So Landin also invented a data structure called a closure that takes the definition and the current environment and wraps them together in a single value. So I left out some detail in the previous slide. By the time a definition is called, it's already been evaluated to a closure that has all of the variable bindings it needs to make sense of its body. Now I won't go into any more detail, but essentially environments and closures are why the SECD machine is faster than our expression rewriter. Happily, you can pretty much just write down the SECD machine's transition function in Ruby. This is a direct translation from the definition in the paper, with extra cases for evaluating closures and constants so that our technique for converting the results back into native integers works properly. It's definitely possible to write this more efficiently in Ruby by doing all the stack manipulation operations imperatively, calling the push and pop methods to destructively mutate the arrays rather than using pattern matching to do it in a purely functional style. But this is a bit messy and doesn't correspond quite so nicely with the original paper. Here's the SECD machine working. It's actually quite a lot faster than what we were doing before. It takes about 3 minutes to finish rather than 2 hours. So that's about 40 times faster. So that's a good improvement. But can we make it even faster than that? Well, yeah, because the SECD machine is a pretty simple loop with a switch statement inside it, it's not too challenging to re-implement it in C. I can just about remember enough C to do that. And then we can compile it down to native code instead of running it as interpreted Ruby, which should make it faster again. In C, we can declare a struct for representing an expression, which can be a variable, call, definition, closure, or constant, and structs for representing the stack, environment, control, and dump. These are really just 4 different flavors of linked list to keep things simple. In a more efficient implementation, we'd allocate our own heap and store these contiguously as an actual stack so that we can just move a pointer up and down as it grows and shrinks. Then we can translate that destructive version of the evaluate method into C pretty directly. It's got cases for how to handle the 5 kinds of expression and the mechanism for updating the state when we apply a receiver to an argument. To keep this code simple, it doesn't free any of the memory it allocates for environments or closures or new expressions, so in production code we need some kind of garbage collector to clean that up, but that's a completely different conference talk. If we compile that C code into a dynamic library, we can use the FFI gem to connect it to Ruby. We just have to tell FFI what the C data structures look like and which C function to hook up as a Ruby method. And we also have to write some helpers to convert Ruby abstract syntax trees to and from C structs so that we can pass them in and out of the evaluate function, but that's boring, so I'm not going to show it. Here it is running FizzBuzz. This time it finishes in 1 minute, so it's 3 times faster than the Ruby version. Now that's not a mind-blowing improvement because the Ruby version was already relatively efficient, but it's still pretty good. So we were thinking about, could we make it faster and even faster than that? And yeah, we can. Firstly, by switching from a tree walking interpreter to a virtual machine, and then implementing the main loop of that machine in C instead of Ruby. Here are what the timings look like. It's a bit hard to see the detail because the AST interpreter is so much slower than everything else. So let's zoom in a bit. which shows that the SECD machine is starting to get close to the performance of RubyProx, but is still about 3 times slower than what we started with. Of course, this leads inductively to the obvious question, could we make this even faster still? Well, I don't have time to show that now, but yes, there have been decades of subsequent work on how to make the original SECD machine faster. For example, during execution, it dynamically translates the original expression into a list of commands, but it's easy to do that work ahead of time instead and compile the expression into commands in advance, which then allows the machine to run a lot faster and avoid the work of retranslating the bodies of expressions that get evaluated multiple times. And to go further, once we have a list of commands for the machine to execute, we can translate each one directly into C or native machine code to avoid the need to interpret them at all. Follow the link at the end of the video if you'd like to see how all that works. But what we've seen here are the first baby steps towards implementing a compiler for a simple functional language. And all those decades of research since the SECD machine was invented have uncovered many more tricks and optimizations we could use to make that compiler extremely efficient. 10 years ago, I concluded Programming with Nothing by asking, why? What's the point of all this? On that occasion, I said that we'd seen a tiny language which had the same computational power as Ruby despite being extremely minimal, and that the only fundamental difference between that minimal language and full Ruby is expressiveness, not power. And what makes Ruby special to us is its particular flavor of expressiveness and how it chooses to balance that against other concerns like performance, safety, simplicity, and so on. So to answer the same question now, having previously seen how to write programs in a very restricted language, today we've seen how to actually implement that language for ourselves. And now we have the recipe for building and using our own programming language with the minimum features necessary to perform Turing-complete computation. The previous talk showed that this language was sufficient to write any program. Today we've seen that it can also be implemented in a couple of pages of code. And from this realization springs an entire history of implementations of functional languages, many of which are more or less an optimized and feature-enriched version of what I've just showed you. What we've seen here is just the beginning. A simple idea like the SECD machine is the starting point for a journey of iterative improvement that lets us eventually build a language that's efficient, expressive, and fast. All right. That's everything I wanted to show you today. I'm aware I didn't give you enough time to properly understand or even necessarily read any of the code I showed you, so it's all up on GitHub if you want to read it and play with it and get a feel for how it works. I hope you found some of that fun or interesting. If not, I'm sorry, but I still really appreciate your time and attention, so thanks very much for watching.